Morning. I want to talk a little bit more about series, converging series. I guess I'm kind of in 9.2 through 9.6 in our book. I've got some problems here, partially worked out. I'm going to finish them here for you and compare and contrast a couple ideas here. But so to start off with, I've got two problems here. And this is kind of my list of tests that I've learned, okay? So there's the Nth Term Test, the sequence of partial sums, the geometric series, the integral test, the P-series test, and the ratio test. Now remember, there's a few in the book that I skipped. Now, so I've got a formal proof of whether these converge or not here, but I want to talk informally for a minute. You know, look at this guy is the series of 1 over n squared plus 4. This is an n squared minus 4. Looks pretty similar. This starts from 1 to infinity, 3 to infinity. But I just want to tell you, they both look a lot like n squared, 1 over n squared. And 1 over n squared is a classic P-series. When P is greater than 1, P is n squared, it converges. So classic P-series, the sum of 1 over n squared converges. And these look kind of like n squared, you know, they're not. Technically with that minus 4, it's not a P-series. Technically with that plus 4, it's not a P-series. But I'm telling you, they act like this P-series, and they converge. Now, that's not formal, that's informal. But I'm going to go ahead and say this guy converges and this guy converges, because that is the answer. But again, not a formal proof, very informal. What I'm doing is I'm comparing it to a known P-series that converges. And I did skip those comparison tests. So in the book, there's some comparison tests that allow you to compare to known converging series. I skipped those, but I'm informally using those to tell you, to preview that these answers both converge. I hope that made sense. Now, officially, what I would do on this one, actually, to officially prove it converges, is I would do an integral test. Technically, to do an integral test, it's got to be decreasing, continuous, so it is. Anyway, here we go. I rewrite this as an integral from 1 to infinity. And now it's an improper integral of x squared plus 4, 1 over x squared plus 4. So, to make it proper, an improper integral, you take the limit as a goes to infinity, you make it 1 to a of 1 over x squared plus 4. Now that is a famous integral. That is the arctangent integral. So the answer is the arctangent of x over 2. X over 2. With a 1 over 2 out front. So the answer to the integral is 1/2 arctangent x over 2. We're going to evaluate from 1 over a. We're going to take the limit as a goes to infinity. I plug in my a, I got the arctangent of a over 2. I plug in my 1, I got the arctangent of 1/2. And I'll help you finish this. The arctangent of a over 2, as a goes to infinity, that's kind of like the arctangent of infinity. It seems like we had a discussion on this once. You can either use the arctangent graph to think about that, or the tangent graph to think about that. But as the arctangent of infinity, as a approaches infinity, arctangent of infinity approaches pi over 2. So this is pi over 2 times 1/2. The arctangent of 1/2 is just a number. It's an angle. I'm looking for the angle whose tangent is 1/2. It's not a famous angle. I punched it in my calculator and I got a 0.464 for the angle. That's in radians times 1/2. But the point is, I've got a number here. I've got pi over 4 minus this number, 0.232. That's rounded off. If I just decimalize this and rounded this, I get an answer of 0.553. And when an improper integral has a numeric answer, we say the improper integral converges. And if the integral converges, the series converges. That's what the integral test says. So we get a number, the integral converges, therefore the series converges by the integral test. Now, one word of caution here, the one reason I wanted to do this problem is, this integral, you could talk about the area under the curve. You could say this is the area under the curve. It's an infinite, unbounded area, but it has a finite area. And you can say that the integral converges to this number, but we do not say that the series converges to this number. So that's a little technicality. I wanted to caution you about that. I'll put the word caution here. The integral converges. You could even say the integral converges to that number, but please don't say, and the fact that the integral converges tells me the series converges, but please don't say the series converges to that number when you use the integral test. It doesn't. We don't know what the integral converges to. In fact, with all these tests, with most of the tests we learn, we don't know what the integral converges to. There's only two that we do. If we ever do a sequence of partial sums, the answer to that is what the series converges to. I think I misspoke a second ago. If we do a geometric series, we've got a formula that tells us what the series converges to. But most of these others are tests that tell us whether the series converges or diverges, but we don't know what it converges to. That's an extra bonus that you don't get with a lot of our tests. But with these two, you do. You know what the series converges to. So anyway, integral test, prove that this converges. Don't know what it converges to. This one, I decided I think I can do a sequence of partial sums. Remember, that sequence of partial sums is a good one to do, so I wanted to help you with that. It only works well when it's a telescoping series. And to see it be a telescoping series, what you have to do is this little bit of work, this partial fraction decomposition. Because that denominator factors, as opposed to this one, we couldn't factor. Because this denominator factors, I could decompose it into two separate fractions. I didn't show you the work, but A turns out to be 1/4, B turns out to be negative 1/4. You could confirm that. And therefore, I've rewritten this as 1/4 over n minus 2 and negative 1/4 over n plus 2. I've rewritten this as 1/4 over n minus 2 and 1/4 over n plus 2, negative 1/4. I factored out the 1/4 actually, and this is now my series, same series, rewritten, and now I can analyze the sequence of partial sums. So you build up this Sn. I started to do it, and then I'll finish it with you here. What you do is you are summing the first n terms of the series, and then that will be the nth term of the sequence of partial sums. Little funny, but here we go. There's a 1/4 out front, and then I plug in the 3. When I plug in the 3, I get the sum of the first term, which is a 1 over minus 1/5. I don't combine those because I want to see what happens. Now I plug in the next term, 4. When I plug in a 4, I get 1/2 minus 1/6. Now I plug in the next term, 5. I'm going to partially sum the series. I plug in a 5, I get 1/3 minus 1/7. The next one is 1/4 minus 1/8. The next one is 1/5 minus 1/9. The next one is 1/6 minus 1/10. And then dot, dot, dot. Way down at the end, you're plugging in an n. I'm just going to say you get 1 over n minus 2 minus 1 over n plus 2. This is the nth term of the sequence of partial sums. And the fact that it telescopes is what makes this doable here. Telescope meaning it collapses on itself. Let's look for this. You know that negative 1/5? It's going to cancel down here with that positive 1/5. That negative 1/6 is going to cancel with that positive 1/6. That negative 1/7, it's going to cancel with the next. There's a 1/7 coming, I guarantee you. And that negative 1/8 is going to cancel with the 1/8 coming. That negative 1/9, it's going to cancel. A lot of stuff's going to cancel. Somewhere down the road, somebody down here at the end cancels. I don't really care to get too technical there. What is left, what you're really looking for, is the terms that don't cancel, which is this 1/4 is out front, remember. And the terms that don't cancel is the 1, the 1/2, the 1/3, the 1/4, and like I said, somebody down here on the end. It doesn't matter too much, but what we've just built is the nth term for the sequence of partial sums. And to tell if a sequence converges, you take the limit as n goes to infinity. So when I take the limit as n goes to infinity of this nth term of this sequence of partial sums, this term goes to 0. And the answer is 1/4 times these numbers. When I add those numbers up, I picked up my calculator and did that. I got 25/12. When you multiply that times 1/4, the answer is 25/48. So the sequence of partial sums converges to 25/48. So the series converges to 25/48 by the method of sequence of partial sums. I'm just going to say that here. It converges by the sequence of partial sums method. And not only do I know it converges, I know what it converges to. Maybe I should say that. Converges to 25/48. All right, that was fun. That was a lot of work. Hopefully you can digest those ideas. Good luck.